Greetings to all the viewers. Now the topic is regarding Diels-Alder reaction. It is the part of organic named reactions. We are dealing with the series of sessions based on organic named reactions. All are available at the channel called World of Conceptual and Competitive Chemistry. In addition, we already gone through engineering chemistry, environmental chemistry, intermediate chemistry, graduation, post-graduation, research-oriented content. Everything is available at the channel World of Competitive Chemistry. So you can subscribe the channel, you can watch regularly and share with your friends so that you will get the sound knowledge in the field of chemistry in the perspective of academia, research and competitive examination as well. The content Diels-Alder reaction was taken from the textbook of organic named reactions authored by Dr. Kavitha Kotthireddy, Kota. Let me describe this Diels-Alder reaction. Diels-Alder reaction is a part of photochemical reaction. It is taken in the light conditions, so that it is called photochemical reaction. It is 4+2 cycloaddition process of conjugated diene systems. So 4 pi electrons containing system is working like a dienophile, and 2 pi electron system both are supposed to be combined. Cycloaddition between the conjugated diene containing 4 pi electrons and dienophile that is having 2 pi electron system. So that combination of 4 pi and 2 pi, that is called 4+2 cycloaddition taking place. So that here the product is 6-membered ring formation. It's a part of it's a part of pericyclic reaction, and moreover the reaction mechanism exact path is uncertain, so that we can say it is the concerted mechanism, and proceeds through the single step mechanism. Need not to go for the multiple multiple steps in order to finish up the reaction. Within the single step the reaction will be accomplished, and Diels-Alder is said to be having multiple applications. The reaction and research of Diels-Alder reaction got explored in many fields, so many applications, so many synthetic applications and biologically important materials introduced via Diels-Alder reaction. So the Diels-Alder reaction is the most emerging trend in the field of synthetic organic chemistry, especially in the named organic chemistry. In order to understand this Diels-Alder reaction well, I am taking conjugated diene called 4 pi electron system 1,3 butadiene. I need to be mixed up with the olefinic compound with a 2 pi electron system. So here ethene was taken as another reactant. This is called diene and this is called dienophile. Diene, upon reacting with dienophile under thermal condition, being it in a concerted mechanism within the single step reaction is accomplished, and concerted we are not able to imagine how the mechanism is proceeded, and finally cyclohexene could be the final product with one double bond. So initially you can count the number of double bonds here, 1, 2, and in another starting material 3. Total 3 pi bonds are there. After this ring formation only you can notice 1 pi bond. So 2 pi bonds are participating in the sigma bond allocation between this carbonatum of dienophile, carbonatum of diene with the carbonatum of dienophile, so that ring annihilation taking place. 2 pi bonds are taking part of sigma bond formation, and 1 pi bond is the part of again another pi bond formation. This is the reaction called Diels-Alder reaction. 1,3 butadiene reacted with ethene. Simply it is the cycloaddition process, and the cyclohexene could be the final product. So it is a part of pericyclic reaction. 4+2 cycloaddition is taking place in this, and cis dienophile is more suitable for this kind of reaction, and ultimately cis product formation is generated. If you are taking trans dienophile and subsequent trans product, that means a steric retention you can observe. Whatever starting material you are taking, even in the final product also stereochemistry will be retained. Stereochemical retention, that is called as stereospecific in nature. Thermally allowed condition, being it is a kind of pericyclic reaction, so that reaction is accomplished in the by rising temperature, so that heating conditions are sufficient in order to accomplish the reaction. Obeys Woodward-Hoffmann rules. So Woodward-Hoffmann rules are there are certain guidelines. In accordance with these rules only the reaction will be proceeded. No catalyst is required, being it is a concerted mechanism and addition process, and heat is the facilitator over there. Instead of catalyst, you can perform the reaction, often accelerated by heat and Lewis acids, AlCl3. So such Lewis acids can be taken, ferric chloride, AlCl3. All these compounds are able to facilitate the reaction, but not necessary. The heat is compulsorily required in order to accomplish this Diels-Alder reaction. If you want to observe about conditions for this, thermally temperature is most important. Around 200 degrees centigrade heating is required in order to obtain this reaction, and Lewis acids to activate dienophile especially. And the solvents are mostly aprotic solvents are suitable over there. Non-polar solvents you can choose either benzene or toluene like this, so that the reaction is smooth, being it is a non-polarizable mechanism. No heterogeneous charges, no charged intermediates. That's the reason why non-polar solvents are more suitable for this Diels-Alder reaction. If you want to understand the reaction mechanism for Diels-Alder reaction, it is said to be concerted mechanism. And within the single step, how the breaking of bonds, how the making of bonds are taken place, that is totally simultaneous manner. Highest occupied molecular orbital of diene interacts with lowest unoccupied molecular orbital. HOMO of diene, LUMO of dienophile are taken for the reaction, so that here the new sigma and pi bond allocation is possible. Ultimately, 6-member ring system is established with one double bond within. Here the detailed mechanism is provided for the entire understanding of Diels-Alder reaction. I am taking 1,3-butadiene, where the 1,2 bond is supposed to moving in this direction in order to make 1,6 sigma bond allocation, and 3,4 pi bond is moving back edge like this, and here the new establishment of pi bond is possible if you are taking dienophile. Among this 5,6 carbon atoms, whatever pi bond is located, that is moving in this direction. This is the reason why there is a kind of bond formation and bond cleavage in a simultaneous manner, and whichever bond delocalized, that the newly formed bonds are indicated in the blue line. So you can notice 1,6 sigma bond newly formed, and 4,5 sigma bond newly formed, 2,3 pi bond newly formed. So all these bonds are newly formed, indicated with the blue color for your distinguishing factor. And the same compound is also go with the anti-clockwise bond allocation. So if you are going with this pi bond toward this side, what happened? Here the double bond will be located. If this pi bond is moving toward this side, new sigma bond is located, and this pi bond ultimately will go there. 1,6 sigma bond will be there. So either of the direction, either you can move in a clockwise or anti-clockwise, both are according same product over there, but the dimension of shifting is different. Here are plenty of examples, being the Diels-Alder reaction explored much more by the scientists, being the reaction is most green protocol aligned kind of mechanism, and most atom economy you can observe over there. Highest yield formation is possible with this, and concerted and short span of the time required, and no need to go for the sophisticated laboratory infrastructure in order to accomplish this reaction, being it is taken at a simple heating mantle only. That is more sufficient for the Diels-Alder reaction. That's the reason why much more research, subsequently much more examples you can notice under this Diels-Alder reaction. I am taking simplest one. 1,3-butadiene is supposed to be added with ethene molecule upon heating, so that cyclohexene could be the final product. So here I am taking one of the electron releasing group over this dienophile molecule, and it is said to be propene. 1,3-butadiene remains similar, so they are supposed to be heated and cyclization taking place, giving rise to one of the substitution on cyclohexene, that is methyl substitution, right? With respect to this carbon atom 1, 2, 3, at the third position methyl group is located, and after getting that one, this is the most important and most familiar example under this Diels-Alder reaction. I am taking methylation over this 1,3 butadiene at the position number 2, which is called isoprene in general. Isoprene is supposed to be treated with this furan dione. Furan dione is supposed to be treated with this one. Here is the double bond which is in conjugation with another double bond. Here is the double bond which is dienophile. These are reacted together, so that already one ring system with the 5 member is there. This is going to fuse with this one, so that here you can notice 6-membered ring directly fused with the 5-membered ring with this cyclic lactone system. Right. This is the way examples are provided pertaining with the Diels-Alder reaction. In order to accomplish Diels-Alder reaction, we need to perform certain prerequisites over there. Diene must be cis configuration or orbital overlap. So cis configuration is more preferable. Cis configuration is more preferable in order to accomplish this Diels-Alder reaction in terms of diene. Diene must be in cis position. Dienophile, usually electron withdrawing group. Whenever dienophile is added with electron withdrawing groups containing ester, containing nitrile, so it is becoming more reactive, so that reaction takes place in the faster pace. Substituents whichever present also influence the rate of reaction, so that effect of substituents on the Diels-Alder reaction process. If you are having diene, electron releasing groups are more important to present over, like alkoxy, hydroxy, amine and methyl functionalities. All these are having the tendency to release the electrons to the diene, so that it is becoming more electron rich. More electron rich species is having nucleophilic in nature. That's the reason why upon the diene, electron releasing groups are much more requirement for this Diels-Alder reaction to proceed. Increase the electron density in the diene. Diene whichever present electron density if increases by these electron releasing groups, so that here highest occupied molecular orbital is having richness in that electron accommodation. Stronger the overlap between the LUMO and dienophile accelerate the reaction, right? So here whenever lowest unoccupied molecular orbital is taken, that is going to react with diene, so that here reaction is the faster pace, being it is a concerted mechanism, within fraction of second reaction will be finished. Whenever we are having 1-methoxybutadiene, this is electron releasing in nature, so that it is becoming active. Conjugated diene is becoming active. This is methoxy substitution giving electron pair to this butadiene. So the reaction of methoxybutadiene is in the faster pace in comparison to the simple butadiene molecule. This is the comparative study of rate of reaction of this Diels-Alder process. I'm taking electron releasing groups over there. Obviously it will go with the reaction with any of the molecule, like malic anhydride. So here the reaction, this is a dienophile, this is diene, are going to be treated. So biannular system will be originated. Alkyl group remains at the position same. The rate of reaction will be obviously higher, being electron releasing on a diene. Electron withdrawing on dienophile will favor this Diels-Alder reaction. And here you have hydrogen only. Hydrogen, what it will do? Hydrogen is not having that tendency to release the electrons in comparison to methyl and methoxy, right? That's the reason why its rate of reaction is somewhat comparatively low. And if you are observing methyl functionality over this diene, what it will do? Releasing tendency will be there. It will activate diene, and it will become more nucleophilic in nature for rising that highest occupied molecular orbital, so that here the rate of reaction somewhat accelerated. Let me go with this methoxy functionality. Methoxy is also having that electron releasing tendency. So this is having richness over the oxygen atom. Electron releasing tendency will elevate its energy, and it is become excited towards dienophile, where electron deficiency you can locate. That's the reason why the reaction is still more for this one. If you observe relative rate of all these comparative study, hydrogen is having rate of reaction only 1 unit, and a methyl substitution will increase by the 4.8 units. If methoxy group is allocated for this 1,3 butadiene, 32 times the rise in the rate of the reaction, you can notice. This is the way comparative study is provided, how the electron releasing groups will uplift this Diels-Alder reaction. Simple reaction, 1,3 butadiene is supposed to be treated with this kind of double bond. So cyclohexene could be the product. Blue lines indicated for the newly established bonds. These two blue lines are the newly formed sigma bonds, and this will be the newly formed pi bond. Relative rate of the reaction will be only 1 unit, being it is all the molecules are unsubstituted. Let me introduce nitrile over this dienophile, where electron withdrawing nature of this dienophile will increase the deficity over the olefinic double bond. Whenever deficity is more susceptibility for the reaction with diene and giving rise to a kind of cyclohexene nitrile, whose reaction relative rate will be 10 to the power 5, exponentially raised. There is extreme change in the rate of the reaction. You can notice that simply due to that introduction of electron withdrawing group on this olefin. This simply indicates what electron releasing groups favors this diene for the faster pace of the reaction, and electron withdrawing group on the olefin will lowers that rate of reaction of dienophile. This is about this relative rate comparison of kinetics of the reaction, Diels-Alder reaction. Again, we are going to treat some new kind of perception regarding the Diels-Alder reaction. Instead of OH molecule, let me go for the cyclic molecule over there. I'm taking furan and about to treat with malimide. Malimide is supposed to be treated with this one. Here is the double bond, whichever present, working like a conjugated system, and this double bond is working like a dienophile. These three are responsible for Diels-Alder reaction. These three pi bonds are responsible for Diels-Alder reaction. Ultimately, here the oxygen whichever present remains as like this, and here the new bond you can notice with this carbonatum to this carbonatum that is there, and here this carbonatum to this carbonatum that is also located, and whatever the remaining functional groups like C double bond O, NH C double bond O, C double bond O, NH C double bond O remains as such. Ultimately you achieved the adductor. So Diels-Alder reaction, diene dienophile whenever combines, cycloaddition concerted mechanism is proceeded, giving rise to the product which is called adductor. So here is another environment. You can notice here the diene present within the same molecule, and dienophile is also located within the same molecule. This is regarded as a intermolecular Diels-Alder reaction. Within the same reactant, both the possibilities like diene and dienophile are located. Let me go for the chemical reaction. Simply it will go with the cyclization in this manner in one direction, either clockwise or anti-clockwise, giving rise to a kind of new ring system in between. So here 3-membered fused ring system, phenanthrene skeleton is located over there with the saturated piperidine over there generated. This is because of what? Intermolecular Diels-Alder reaction. This is the simplest example. These many possibilities why we are observing, because this much research already conducted based on Diels-Alder reaction. Here is another molecule very linear in nature and having some puckered nature. Puckered ring system is located. Only our focus is purely upon this diene and dienophile. Here is the double bond conjugation, and here is the olefinic double bond, and moreover methyl is located on this dienophile that is not yet all favorable for the cyclization process, and the yield could be somewhat less, because always dienophile should be accompanied by this electron withdrawing group. Rather you noticed electron releasing group. This is not favorable actually, but the reaction is proceeded. Anyway, all the molecules are in the synchronized form and about to react very fastly. That's the reason why ultimately we got this 1, 2, 3, 4 member ring system. This is exactly the skeleton of steroids. So steroids also synthesized by means of Diels-Alder reaction. Earlier we gone through this the molecule said to be alkaloid, or else you can also treat it as a basic compound. like a heterocyclic compound as well. And here purely you synthesize the steroid within the laboratory. This is also another advanced application pertaining with the Diels-Alder reaction. Now we entered into the conclusion part by stressing the application purview of Diels-Alder reaction. Cyclic compounds anyway generated by this process, we are going to cyclize the diene with dienophile molecules so that natural products, so many can be, and pharmaceuticals like potential drug curate is also generated by means of this Diels-Alder reaction. Synthetic rubbers manufactured by this one, Bunais, Bunai and thiopol rubber, everything will be there, right? So they're also having the condition over there, cyclohexene derivatives are taken, cyclohexene related derivatives can be synthesized which are having that synthetic rubber properties. Total synthesis complex natural products like steroids just to be gone through, and alkaloids also synthesized by means of this Diels-Alder. Examples we already noticed. Polymer chemistry also linked with this Diels-Alder reaction, cross-linking in order to make linkage between the two growing chains. If you are making such a cross-linking, there is also the possibility for this Diels-Alder reaction. So the Diels-Alder reaction is everywhere. Important in industrial process in order to manufacture insecticides, and the fragrance is also manufactured by means of Diels-Alder reaction containing that cross-linked products. So by this successfully we concluded the application purview regarding the Diels-Alder reaction. So many important applications are observed for Diels-Alder reaction. Now let me go with the examination perspective, competitive examination perspective. What questions we will expect from this topic called Diels-Alder reaction? If the reaction is thermal, we obviously 200 degrees required in order to make the new bonds, in order to break existing bond. That's why the reaction is thermokinetic conditions. Diels-Alder reaction allowed under the suprafacial 4+2 cycloaddition. Suprafacial and the same side reaction is accompanied. So 4 pi electrons of diene and 2 pi electrons of dienophile are supposed to be treated, and addition reaction taken place, giving rise to annular system, ring system. Aromaticity is perfectly balanced. Transition state will be 6 electrons. Aromatics of transition state is also allowed over there, so that aromaticity of the transition state will be 6 electrons. By this we completed the entire concept of Diels-Alder reaction. We will come up with a new topic in the next session. So here whatever we discussed, the entire in-depth concept regarding the Diels-Alder reaction, how the reaction we can designate, and how it could be the mechanism for the reaction, and what is the origin for this one, and how many possible examples we noticed, and finally what could be the applications for this Diels-Alder reaction. Everything is available in this session. Hopefully it is informative and gives the worth knowledge to the viewers whoever serious about the chemistry. Definitely you will get the success what you are aspiring for if you follow the channel regularly, and avail the content whichever available in world of conceptual and competitive chemistry, and also share with your friends so that we will get the new topics every day. This is presented by Dr. Kavitha Kotthireddy, Kota, Professor of Chemistry, academician, researcher, author and reviewer. Thank you very much. Thank you one and all for your patient listening. You can subscribe the channel, you can watch regularly. All the kind of content is available over there. So signing off, Dr. Kavitha Kotthireddy, Kota.